So continuing with chapter 5, we've talked through all the information that I'm expecting you to know. The vocab in the background that goes along with quality assurance. And then the two calibration methods that are extensions going beyond what we understood about calibration, what we learned in general chemistry about calibration curves, where we can make a calibration curve by taking standards of known concentration and testing them, making a nice happy graph with a 0, 0 data point and a bunch of other data points compared to the response. Again, your examples were mostly calibration curves with spectrophotometry. So like the y-axis was absorbance and the x-axis was molarity or some concentration. And then based on the best fit line, you're able to use the slope for that to solve for the unknown concentration. Like then you have an unknown solution. You don't know what its molarity is, but you can solve for it using that graph. Okay, so that's the straightforward direct calibration. The two scenarios we looked at in this chapter were when that doesn't work, when you don't get a linear response, when there's too many things going on in your unknown mixture that you can't identify the analyte, we can do either standard addition or internal standard. And what you're going to be expected to know out of this, be able to read a problem and recognize which one is being used, or for you to define it to me, like know what standard addition means, know what internal standard means, okay? And then also, if I give you problems, being able to recognize it and then solve mathematically using either one of these methods. I'm not going to give you a scenario where I say, this isn't working. What should I do? We're not there yet, buddies. We're not there yet. So right now, it's just, what is standard addition? Solve if it's standard addition. What is internal standard? Solve internal standard. So what we're going to do here, this last video is not new information. Got some more examples, and by more I mean there's 2 more examples. We're going to read them, identify what type it is, and then do the math. Now what I did do was make these a little bit more real life, which is there's some additional parts to it. Not anything that's new, but things that we would like real life chemistry when you have to do another dilution or something. So we're gonna look at those. So honestly, for this, we're gonna read it together, and I'm gonna kind of pause. I'm hoping that, well, we'll get there. But these are supposed to be, I want you to have blank paper and your calculator and your pencil in front of you, because I actually want you to try these, and then we can compare what you do to what I do and see how that went. So example number 1, we're gonna read the problem. A urine sample is being tested for the concentration of phosphate ion. 2 milliliter urine sample is diluted to 100 milliliters. So, I'm just telling you in real life what that means. They used a 2 milliliter volumetric pipette, added it to a 100 milliliter volumetric flask. 25 milliliter aliquots of that diluted solution gave an absorbance reading of 0.428. Okay, so they took 25 milliliters of that diluted P, and they got an absorbance of 0.428. A second aliquot of 25 milliliters had 1.00 milliliters of standard phosphate solution, which has a concentration of 0.500 milligrams per liter added to it, and the resulting solution gave an absorbance of 0.517. We're supposed to calculate the concentration of phosphate in the original urine sample, which means all the way back to how much was in the urine sample that 2 milliliters came from. Okay, before we even start trying to math, I want us to stop and think. So I want you to pause and think, which scenario is being done here? Is this standard addition or is this internal standard? So the correct answer is standard addition, and let's talk about why. We're testing our unknown sample for phosphate ion. That's the thing we're trying to solve for. Calculate the phosphate in the original urine sample. Now, when we go back and look at what was the thing that was added on top of it? Well, it was a standard phosphate solution. So the thing we're testing from our unknown is phosphate. The thing we added on top of our unknown was phosphate. So it's the same analyte. So this is standard addition. Standard addition is when you're just adding the same analyte on top. So once you recognize it's standard addition, we have our equations from standard addition, which, and I'm not asking you to memorize our equations for standard addition. That's something that I will provide you with. So I'm going to put them on this slide, and then we'll go forward on the next slide and actually start doing some math. And then I've got for S. Again, I'm using the symbols the way our textbook does, just trying to have consistency with that. So those are the two equations that we're just using M1V1, M2V2. So they weren't really unique to standard edition, but they're useful for it. This is the actual definition equation for standard edition. My brackets are not looking very square today. Okay, so we're trying to use this equation to solve for the concentration of phosphate. And so in our urine, so that's X. So Xi is what we're solving for. How much phosphate was in our original, or was in the P sample that we tested. S stands for the standard phosphate that was added. X stands for the phosphate in the P. Okay, so I'm gonna, well, I guess we can do it here and then we'll just carry it over. Let's take the numbers from the problem and determine what variable they go with. Okay, so 2 milliliters of P was diluted to 100 milliliters. Okay, and then 25 milliliters of that was tested to have a 0.428 absorbance reading. Okay, so when we look at this, that 2 milliliters to 10, that one wasn't, like, we didn't test the 2 milliliters. So I'm going to have to come back to this later. That's like a pre-test information. Then they took 25 milliliters of this and got an absorbance of 0.428. And then they took 25 milliliters of the P sample and added 1 milliliter of the phosphate, which we know it's concentration, and we got our resulting solution. So for our values, well, SI, which is the concentration of the standard, is the 0.500 milligrams per milliliter. Volume of the standard was 1.00 milliliters. And X plus S, when I tested the mixture of both of them, we got 0.517. When we tested the mixture of just the one, we got 0.428. And then the volume of the sample was 25.00 milliliters. 25 milliliter aliquot of the diluted solution. We also used 25 milliliters of that. And so the variable, there's two variables we don't know right now. We haven't written down V and we haven't written down XI. So V is the total volume. So normally this would be like the volume of the volumetric flask. But when we went ahead and made our mixture, they just added 1 milliliter on top of it. So V is going to be the total volume after everything, which is 26.00 milliliters. XI is the amount of phosphate in that 25 milliliter P sample, so that's our unknown. Okay, so what we're going to do is I'm going to take this information, I know it's like disappears, but we're going to go to the next slide and start plugging stuff in. Okay, so I'm going to start with the equation for SF, because we had all the information we needed there. So we need to put SI, which is 0.5, is it 5 or 0.5? 5. And then VS was 1, and V was 26. And I just realized in my notes that I did 0.05 instead of 0.5, so I'm going to redo this calculation on my calculator right now. So I got, let's see, yep, I definitely did it wrong in my notes. 0.019230769 is the molarity of SF. Okay. So let's set up our XF equation. We do not know XI, but we do know V0 is 25.00 and V is 26.00. So we have that. Okay. And then now we have our big standard addition equation. So 0.428 over 0.517 is equal to xi over xf plus sf. So xf, I'm going to write this. I'm going to substitute in we have, and sf, I'm going to write the number 0.019230769. So this is where I don't know that it really makes it that much simpler, but where I usually say xi, from now on, I'm just going to call that x. That's my unknown thing. I'm also going to go ahead and do some of this math. So I'm actually going to take the number 0.428 divided by 0.517. And when I did that, I get 0.827853. Got x on top. Got x times 25 divided by 26. So I'm going to go ahead and do that math. I get 0.9615385 plus this number that's still the same. So then I'm going to cross multiply the denominator of this over to the other side. 0.827853 times x times 0.9615385. My handwriting is horrible. I apologize. 0.019230769 equals the numerator that's left over here. So now I'm going to need to distribute that. So when I do that multiplication, I get 0.796012x plus 0.01592025 equals x. So I'm going to subtract both sides. 0.796012x. I'm going to subtract from both sides. So on the left, that'll leave me with just the 0.01592025. And on the right, it's going to be 1x minus 0.79601225x's, which leaves me with 0.2039875x. So now I'm going to solve for x. And when I get that, or when I do that, I get 0.0780,452. So that's xi. That's the amount of phosphate in the urine sample that we tested. And the phosphate units were milligrams per milliliter. I kind of dropped units as we went because stuff. Okay, so let's go back and look at our problem. So we just calculated xi, which is the concentration in that 25 milliliters that we tested. Okay, now what is true though is, remember how we had the thing in parentheses that was like this is like before we'd made our test. The 2 milliliters of the urine sample is diluted to 100 milliliters, and they used that. Well, so that xi is the concentration of this. We need to know the concentration of that original 2 milliliters. So we're not quite done yet. Xi, I'm going to write in dilute urine is equal to what we had on the last slide, 0.0780452 milligrams per milliliter. But what happened in real life was that came after a dilution. So dilution looks like this. So M1 is going to be the concentration of the original solution. V1 was the 2.00 milliliters of urine they originally added. M2, that's what we just solved for. What was the concentration of that solution? And V2 is not 25 milliliters. That's how much was used when we tested it. When they made the solution, they took 2 milliliters and added it to 100. So 100, so again, backtracking. 2 milliliters was added to 100, or was mixed together up to 100. So when I solve for M1, I get 3.902 whatever milligrams per milliliter. So that was the standard addition problem that started out exactly the same way as the example that we did in the standard addition video, but ended up needing one more step added to it because the problem told us that we did a dilution before we even started. So, fun times. All right, we have one more example. Let's read it. Determine what it is, if it's standard addition or internal standard, and then do the necessary math. So, all right, chloroform is added when determining the pesticide DDT in a polarographic analysis. You don't have to know what that is, it doesn't matter. A mixture containing 0.500 millimolarity chloroform and 0.800 millimolarity DDT gave us signals of 15.3 micro amps for chloroform and a 10.1 microamp for DDT. An unknown solution, which was 10 milliliters, had DDT that contained DDT, was placed in a volumetric flask of 100 milliliters, and 10.2 microliters of chloroform was added to it. After that, the signals were 29.4 microamps and 8.7 microamps for chloroform and DDT. We want to find the concentration of DDT in the unknown. So, lots of words. First, we have to decide if we think this is standard addition or internal standard. So when we're looking at this, in this problem, they measured things for two different chemicals, chloroform and DDT. So that is your hint that this is an internal standard problem. So for internal standard problems, the equation that you would be given, you don't have to memorize, but you would be given AX over the molarity of X equals the response factor times AS over the molarity of S. So that's the information that, I wouldn't give you that in the question. It would be on the given information thing, because part of the question would be you determining if it's an internal standard or standard addition, and then you correctly, identifying which equations are necessary. So in this problem, we have, a couple different scenarios. They gave us responses, so A's, in this sentence up here, and then they gave us A's down here for our second solution, and we're trying to figure out the concentration of DDT in the second solution. And this is how internal standard problems that I give you are going to go, because in the question, you're not going to be given the response factor, the F value. So your first job is going to be to figure out the F value, which means you need to know the other four things. So that is why we were given that first sentence. So I'm going to go ahead and let's find F first. So that's where we're going to start. So for AX, so X is the thing that we're measuring, which is DDT. So AX is 10.1 microamps, and the molarity of X is 0.800 millimolarity. So X equals DDT, the thing that we're supposed to be measuring. S equals the other chemical that we always know about. So the chemical that we're being asked to solve for is going to be X. So equals F times, let's see, the response for chloroform is 15.3, and the molarity of chloroform is thought I read that, where'd it go? 0.500, yeah, millimolarity. So now we solve for F, and when I solve for F, I get 0.412582. So we got F. Awesome. Okay, so we have F. So what we have here, so we have to redo this equation again, plugging in F. We have our response factors, our A's, and then we're solving for X here, okay? So let's make sure we have the information we need. Well, we've got that number, that's for chloroform. We've got that number, that's for DDT. So let's go back up and look at, we're done with this sentence. This sentence did its job. Sorry, it's not over yet. There. This is where we're kind of starting. So an unknown solution, 10 milliliters, containing DDT was placed in a 100 milliliter volumetric flask, and 10.2 microliters of chloroform was added. Okay, because what we need here is we need to know the concentration of S, which is the molarity of chloroform, and they don't directly give us that. Okay, what they tell us is that we take 10.2 microliters of chloroform, where we're given the molar mass and the density of chloroform, and we're told that it's put into a 100 milliliter volumetric flask. So we're going to have to start by doing a little bit of work to solve for S. Once I know that number, we can just plop, 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 solve for X. We just weren't given directly the molarity of our second chemical, which is the chloroform. So what we know about chloroform is that we took 10.2 microliters of chloroform and we diluted it to 100.00 milliliter volumetric flask. And we were told the molar mass and we were told the density. So using those two pieces of information, we're trying to get to molarity. So it's moles of solute on top, liters of solution on the bottom. So the solute is chloroform. So I would start with the 10.2 microliters of chloroform. If nothing else, I'm just going to start by getting rid of the micro. It's a starting place. Now when we go back, we were told the density of chloroform, and that would be a way for me to go from milliliters to grams. So I just went from microliters to liters. I guess I'm going back to milliliters. We'd recognized that earlier. We could have went from microliters to milliliters, but that's fine. And then I'm going to use the density, which is 1.484 grams in 1 milliliter. So 1 milliliter, 1.484 grams of chloroform. Now I'm trying to get to moles on top of chloroform divided by liters of solution. So I have grams. I would next use the molar mass, which was given. It's 119.39 grams in 1 mole of chloroform. So that gets me moles of chloroform, which is awesome. But I need molarity, which is moles divided by liters, and the liters has to be the total. So my total was 100.00 milliliters. So what I'm just going to do, use this entire side, is convert milliliters to liters. And what we have here is 0.00126.784 molarity. So all that work, what we just got was the molarity of S. Okay, so what we need to do, here's our equation for internal standard again. We need to plug everything in to solve for X. So AX, which is in the second part, what we got for DDT. So I guess I'll change colors here. So AX is going to be 8.7 microamps. I do not know the molarity of X. F is the response factor. We solved for that on the previous slide, so just bringing that forward, 0.412582 is the value of F. AS is the response of chloroform, which was 29.4 microamps, divided by the molarity of chloroform, which is what we just solved for, 0.00126.784. We can use our calculators to solve for everything on the right-hand side, use algebra to solve for X. So the value of X, I put it in scientific notation, but 9.1 times 10 to the negative fourth molarity, or 0.00091 molarity. It didn't ask for a specific unit, it just said concentration. So you could have done this in like millimolarity if you wanted. I don't know. Like you could have done it in a different unit, but it needed to be in some version of molarity. So recognizing that this was internal standard, recognizing that this is the equation for internal standard, and then realizing that the problem didn't tell you the molarity of S. It gave you other information that you had to do, dimensional analysis, not stoichiometry, but dimensional analysis to get to the concentration of S. So that was the extra step in this problem, was that I didn't directly give you S. You had to solve for it using things that we learned in like Gen Chem 1 and we practiced at the beginning of the semester. So hopefully things went okay with this. Just let me know if you've got questions, and definitely check out the practice problems in the practice problem folder for these chapters to, try some of these problems on your own.